This tutorial will introduce students how to extract and import the photogrammetry meshes provided by Google in their Google Maps web application into Blender for reference purposes. Please remember that the photogrammetry mesh data here is copyrighted, both by Google and the companies providing Google with the photogrammetry data. So do not use this in any way other than for your own private purposes, as a reference perhaps for the process of your architecture project development. But make sure to adhere to the copyright that this data is presented with. One initial note is also that different areas have different resolution and photogrammetry quality. Here you see our architecture school, but if we go to Basilique du Sacré-Cœur, let's make sure that we disable annotations. Here, if we zoom in, we can see that we have a much more high resolution and higher quality data than was previously shown for the Stockholm one. So the quality of the photogrammetry mesh data will vary depending on location. That is one thing to take note of. To extract and import the photogrammetry mesh data from Google Maps, you will need three things, or three pieces of software. You will need Blender, an eminent tool for practically all 3D needs. You will need a Blender plugin called Maps Models Imported, made by Élie Michel. And you will need a standalone software called RenderDoc, made by Baldur Karlsson. So the first thing you should do, if not already having done so, is to download and install Blender. To do the same with the Maps Models Importer plugin here. And if you click here on releases, on the latest release, we will be using 0.4.0. You see here what versions of the softwares are compatible with this version of the plugin. And you can download the plugin here. To install the plugin, you simply follow these instructions. And RenderDoc, you need a certain version of it, compatible with the version of the plugin that you use. While you can download the latest here, you can also go to other builds here, and you will get to a list of all stable builds. And for this case, we will be using the 1.13 release here. And if you're using 64-bit Windows, make sure that you download and install the 64-bit Windows installer here by clicking and then installing. Having done so, we are ready to inject into Google Maps. Start RenderDoc. With RenderDoc started, go to File and click Inject into Process, enabling this tab here, Inject into Process. And having done so, you can hold the Windows key on your keyboard and pressing R. This will open the Run command here, and then you simply type CMD to open a command prompt with Enter. And with the command prompt open, you copy and paste 2 lines of text provided in the description. One note here is that if you're using a 32-bit Chrome application instead of a 64-bit, then that resides in the x86 program files folder, like that. But for this case, we're going to use the 64 bits, and then it's like that. Pasting the 2 lines of text, I've already executed the first line. So to execute the second line, one would only need to press Enter. But this is important now that since we want to inject into the Chrome application process, that we don't have any Chrome process active in the background. So we'll just close all Chrome windows here. Very good. And then we can press Enter. Now you're greeted with a blank screen, but actually if you Alt-Tab, you will see that there is actually a dialog here that says that graphics processing unit is starting with a process ID of 32392. And this process ID will vary from instance to instance, but this is the process that we are going to inject into. So if you Alt-Tab to RenderDoc, and then click Refresh, and then making sure that all the processes are sorted by their process ID, we can once again just make sure 32392, and then we'll go down to 32 here. 32392, the Google Chrome GPU process. Very good. These match perfectly. Alright, so before clicking OK here, we should inject into the process. So having this process selected, we click Inject here. And now we are injected into the Chrome application process. You see that the connection status is established. Very good. Now we can click OK. So Alt-Tab to this dialog here and click OK. Very good. You see this overlay here as a confirmation that the injection is correct. Very good. And then we simply go here to Google Maps. And we switch the layers from the map layer to the satellite layer. And by clicking on the 3D button here, we make sure that we see the photogrammetry mesh in an oblique angle, so as to visually confirm that we are viewing the photogrammetry meshes. And then we maneuver to our point of interest, and here there are a couple of things to think about. Google uses several different level of details, or LODs, different states of detail, to make sure that the web application can be run in an efficient manner. You see this if you zoom in. You will go to the highest level of detail, but as you zoom out, you will progressively see less and less detail. There we saw that this curve was deteriorated. You see here, from that to there. The mesh that is presented now is less complex than the one presented here. This can also clearly be shown in this corner. When we are this zoomed in, we have a straight corner. But as we zoom out one step, this gets diminished into something that's a little more crooked. If we zoom in once again, you see? Yeah. So your level of zoom in defines the level of detail that Google Maps is showing. I'll disable the annotations here. And when it comes to extracting these photogrammetry meshes, what you see is what you will get. What is currently presented on your monitor will be the photogrammetry meshes and textures that will be extracted. So if you really want the highest level of detail possible, then you should zoom in until you get that level of detail. If you want a very large area covered, then you will have to accept that the level of detail will be progressively less and less detailed. You saw there a large jump from a higher level of detail to a lower level of detail. But that is simply something you will have to accept. If you are adamant that you want the highest level of detail possible for as large of an area as possible, then you can manipulate which level of detail is showing by changing the zoom, not the actual zoom of the camera in the web application, but the zoom level of the Chrome window itself. So I will demonstrate this in the opposite way because it's much clearer. So we'll go in, we'll zoom in here until we have the highest level of detail. Very good. And then if I, with Control and plus on the keyboard, I hold Control and press plus, I will adjust here. Perhaps it's not very clear because of the injection. You see here this little zoom icon. As we zoom in further, it will be, and there it says zoom 125%, and we'll continue to zoom in. And as you perhaps saw, when we zoomed in here, the level of detail turned slightly less detailed. So even though we are very close now, the photogrammetry mesh and texture presented here are now in a less detailed quality than previously at the same camera zoom in, but with a different zoom in for the Chrome application. If we zoom out slightly here, you will see that it immediately turns much less detailed. And this will only be more and more accentuated the further you zoom out here. And having demonstrated this the opposite way, we can do the same way but the reverse direction. So we'll simply Control and minus. Make sure that the Chrome web application is fully zoomed out. I think that full zoom out is 25%, yes. And now you see here that we have restored much of the level of detail here. And with this Chrome zoom level at 25%, we can zoom out much further before the level of detail changes. I think there was the first sign of it changing. And there. So now we are this far out, camera-wise, before that curve got decimated in a lower quality level of detail. So perhaps we can zoom in a little again. So manipulating the zoom of the Chrome web browser is a way to get higher level of detail for a larger crop or a larger area portion. And like stated before, what you see is what you will get. So any photogrammetry mesh that is loaded now into the Chrome application for viewing inside of the Google Maps web application will get extracted. And with the graphical user interface at 25% zoom, it can be quite hard to click on these small icons, but you know that if you hold shift, you rotate the camera like this. If you don't hold shift, you pan it. And if you decide that you, having rotated the camera, you want to return to north pointing straightly up, then you click the compass icon here. And here you see that now it is north oriented again. Alright, so when you have decided upon an area of interest here, perhaps we can zoom in a little. The larger the view and the higher the level of detail, the more strenuous the data will be to process by the computer when importing into Blender. So that is something to take into consideration. Perhaps start with a small portion just to see what your computer can handle and then incrementally go up to the ideal crop. I think that we can test with this here. So having the camera projected as we want, with the level of detail we intend, and of course with the RenderDoc overlay here, making sure that we are properly injected into the process. It says here that you can press F12 or print screen to capture, but F12 will open the developer mode, the inspect page interface, and the print screen we have found is not too reliable either. What has been most reliable for us is to simply Alt-Tab and go into the RenderDoc application here, and then simply click this Capture Frame Immediately. Do this, click this, Alt-Tab and Pan. And as you see, the process freezed, but now it is live again, and you see here that it said Capture Frame 15013. And it should say 1 captured save here. It says 3 captures, since we tested 2 captures that took too long for us to pan. Alright, we can Alt-Tab back into the RenderDoc application, and here we see it, that we have a capture collected. And the easiest way to evaluate at this stage the amount of data you have captured is by simply looking at the file size here of the capture. And 300 megabytes is quite much, and that can be understood in the light of that we used 25% zoom here, as well as being pretty well zoomed out. I would perhaps suggest that if you test this for the first time, go around 100 megabytes, so perhaps around a third of this. So if one would do that, then one would simply change the zoom in level or go zoom further in so as to reduce the amount of data that is captured. But for this example, we will still test with the 300 megabyte data. Alright, going back to RenderDoc. And with this here, we simply click Save here. Clicking Save will allow you to specify the directory and the file name where you want to save it. And save it. Very good. And for us, when importing this into Blender with the Maps Models importer, it has been most reliable to make sure that RenderDoc is not injected. And the easiest way to do that is to simply exit the application, as well as the Chrome window. With the RenderDoc capture document saved in an appropriate directory, we can open Blender. And here, after simply deleting those things in our custom starter file, the main thing is to look into the preference, and in the add-ons pane here, make sure that you search for Maps Model Importer and make sure that this is active. This checkbox is checked. Very good. Then the next thing is simply go to File, Import, and Google Maps Capture. Go to the directory where you saved it, and to import it, click the Import Google Maps Capture file. the only option you have here when importing is the maximum blocks, and the -1 or 0 is an infinite number of blocks. But if you are just testing out, since this is a large file, 282 megabytes here, you could actually test it out by simply, let's make it 50 blocks. Then it will only import the first 50 meshes and be satisfied with that. So we can click here. Let's wait for the process. This might take quite a long time, but for only 50 meshes, that took less than a minute. And they are positioned around the origin, but as here, they might be very small, so we can simply click the comma or period numpad key, depending on your language locale. For Swedish keyboards, it's a comma, but it might be a period on your numpad. That will immediately zoom in at the selected objects. And we zoom out here a little, and we see here that these 50 first objects were not at all interesting, of course, or not of course, but these turned out to be really uninteresting, but it's a lot of foliage and it's a little part of a building here. If we change to rendered viewport shading here, we can just get a glimpse of it working or not. Very good. I'll just quickly make sure that we have a transparent background so as not to make the Nobel Park here our background. Very good. Looks like we expect. Then we can, with A, the A key on the keyboard, and X, the X key, we can delete everything, and then we can do it again. But now we have -1, an infinite number of max blocks, and this will take quite some time. Click Import to import, and be ready to wait for a long time. Alright, so having waited, I think it's almost 40 minutes of processing time for this 300 megabyte file, so there's another reason why one would initially start with a smaller file. But now we see that the scene outliner has been populated with hundreds of tiles or meshes. As well, we can see here in the viewport that we have lots of objects. And to zoom in on these, one could press A on the keyboard to select everything. One noticed that it was quite sluggish, so perhaps that's not the wisest maneuver to make. But having already selected all those, we can press period or comma on the numpad keyboard. And we can zoom in here, and I'll hold Alt and press A to deselect. And this looks like expected. Of course, this is not showing with the textures. In the solid shading mode here, one could actually click texture, which will incur, of course, another waiting time, but not that serious for one. And here we can see what the photogrammetry mesh looks like textured as well. If one changes shading mode to the material preview or even rendered, we can see here the result of the import. The photogrammetry meshes come imported as these individual pieces, either as some sort of para tile or as simply individual pieces like this. And it can be recommended to reduce the complexity of the imported model here to simply press A on the keyboard to select everything. And you see here the one with the light orange highlight, that's the active object, and that will be the target if you join all of these meshes here. So I'll hold Control and press J and wait for the join command to compute. Alright, and I think it was over 4,000 objects that were joined, so it would not have come as a surprise that it took close to 4 minutes to join all those objects. But now we have one object consisting of all the imported photogrammetry meshes. This is a very, very large object. It would be advisable to save the model as it is now before doing any further manipulations. Perhaps one could have done it already before the join command as well, but let's save the file. If you are in a directory and want to make another folder, you simply press I on the keyboard. That's a new folder for you. Blender. Save. Right, after saving, one can, with the object selected and active, we can press a tab key on the keyboard. That will enter edit mode, as you see here. And now we have 3.4 million vertices. That's very, very many. And since all the meshes were imported as tiles and portions of the objects situated side by side, we can save some complexity or reduce some complexity by simply, if we change here to vertex mode, see the vertices more clearly. And with everything selected as is, we can press the M key on the keyboard, and then we can collapse or merge these by distance. With a default value here of 1 micrometer, we saw here that many vertices were merged on the assumption that they were in the same position or 1 micrometer in this arbitrary scale, close to each other. And we see here that we reduced the number of vertices by almost 1 million. Alright, so we'll accept this result. Otherwise one could change or tweak the merge distance here, but we find it perfectly adequate, reducing the complexity of the model of more than 25%. We can click tab again to exit edit mode, to object mode here, and we can save the file again. Now, the next thing is that this model, it uses one individual material for each and every imported mesh. So if we check here in the material pane here, so we have thousands of materials here. And we want to make sure that we only have one material, because now if we enter edit mode here, and having entered edit mode with the tab key, if we select face selection mode, and if we Alt A to cancel the selection, we can see here and with this first material in the list here, selected, and if we click select here, we will select in the scene. Yeah, and that was, of course, the object that we chose as active. So that's the root object for all of these merged objects. But as you see, and if we click here and select, I think it will expand the selection. Yes, that's so. And here, so if we redo that and Alt A first to deselect, and then select, then we can here press the period or comma numpad key to immediately go here, and there you see that these triangles have their own material, and that is really wasteful in terms of resources and the number of and the amount of texture needed to render the whole model. I'll exit edit mode here. So one thing we could do here is to create a duplicate of this merged mesh and project the color values on the originally imported textures onto a new texture that will be assigned to the duplicate objects. So we can first, if we press M on the keyboard, we can move this to a collection, and we can type this as original perhaps. Okay, very good. And then with this still selected, we can hold Shift and press D for duplicate. When you see here that the duplicate object moves, you can simply cancel the positioning of it with the right mouse button click, and it will be in the same place as the original. We can, with this duplicate object still selected, we can press M and a new collection called projected. Very good. Now we have two different collections, one that is the projected and one that is the original. At this moment they are the same, but we will, for the projected one, we can hide the original one so as not to confuse ourselves. Making sure that is the duplicates that you have selected with all the material slots that we want to delete. Then we can switch to the scripting workspace here. And with that still selected, we can simply copy into this pane here the script that is supplied in the descriptions and enter twice. And we have another waiting time here. Right, that took a non-insignificant amount of time as well, so be sure to save before. Let's switch back to the layout workspace here. And by clicking period or comma on the numpad here, we can see here, switching to the material tab here, that we have no material. And you see that also here, of course. There is no material assigned to it. Very good, we can save. Now the next step is to actually unwrap the mesh that we are going to project the original texture color values onto. But realizing here that we have 2.5 million vertices, more than 3 million faces, unwrapping in Blender is going to take too long for such a complex mesh. So improvising here a little bit, we will download MeshLab that has a perfect function to unwrap each triangles in a relatively non-computationally intensive manner. One would not prefer that triangular unwrap for perhaps any other use case, but when it comes to photogrammetry meshes such as this and projecting the color values, then it's perfectly adequate to use. So we'll go to meshlab.net, click download, and download the Windows 64 executable here. We'll install MeshLab. We can run immediately. Alright, to import it into MeshLab, we need to export it from Blender first. So going back to Blender, making sure that we have saved the model before. Very good. We can, with this object to be projected on selected, we go to File, Export as an OBJ. We'll make sure that we export only the selected objects and leave everything at default. Export it. Alright, when the mouse cursor is showing again, you have successfully exported it, and then we can open MeshLab and import it. So File, Import Mesh. Go to the directory where you saved the exported file. Here we have it, the OBJ file. Open it. Very good. And the only thing we want to do here is to simply unwrap it in the easiest way possible. So we'll go to Filters, Texture, and the parametrization trivial per triangle. And now here is the settings for the final texture that you're going to project. And we suggest no less than a 8K texture, but perhaps that's a little too computationally intensive for some scenarios. So, but it's important that you choose a power of 2 here. So if you do not choose a 1K texture, 1024, you choose a 2K texture, 2048, or 4096, a 4K texture, or 8K, 8192. The border between triangles can be left at the default 2 here. And then we simply click Apply. And that was that. And doing that in Blender would have taken a very, very long time, at least if you would have been using the UV Smart Project function there. Close it, and then export it. So File, Export Mesh. And since this is flat shaded, it does not have any smooth shading, any average normals of vertices between the faces. We can simply uncheck the normal value. It is flat shaded from the original imported mesh and will be if no normal value is given for the vertices. We do not need any color since this is the textureless one, but we do need the texture coordinates. Those were the ones that we generated here with the filter. Okay. And this actually did overwrite the imported file that we exported from Blender, just to be aware of that. Otherwise you would have, of course, clicked Export Mesh As, but now we overwrote it. Going back to Blender, we import that. Import an OBJ, this one, the one that we recently modified in MeshLab. And this can be, we can disable image search, and we don't need any smoothing groups. Those are pertinent to the normal values, but now we don't have any custom normal values. Alright, we'll import the OBJ, and we'll allow it to import. Very good. It is now imported again, and as you see, there are many overlapping regions which result in these Z buffer fighting, but that is totally expected, since they are the same, except that the now imported one from MeshLab has properly unwrapped texture coordinates. In light of this, we can actually select the previous one, the projected but not properly unwrapped, and delete this. And then we can select this freshly imported one and make sure to put it in the projected collection here. And we can check out the UV unwrap here if we go to the UV editing workspace with this object selected. Here, with all of the faces selected for the object in the edit mode in this workspace, we can see that now it looks only black, but if we zoom in here, we will see that the largest triangles are here at the top, and then they turn smaller and smaller the further down we get. And this is a very improper unwrap for like any other use case than this static photogrammetry mesh that we're going to project from many previously imported textures. But for this use case, it is adequate. It is perfectly adequate. Right, going back to layout. The next step is to make sure that this material that is now assigned to all of the mesh to be projected, we have to make sure that we create a texture to project on. So we'll go to the shading workspace, and here if we change from world to object, then we make sure that we have the currently selected, the currently active object here. We can press period or comma on the numpad key to go a little closer. And as of now, we don't have a texture here as the base color. So we'll simply hold shift and press A. And then we'll go to texture, image texture. Very good. And we'll click here to make a new image texture. And this should be like we input in the settings for the MeshLab unwrap, 8192 times 8192. It does not need to have an alpha. The background color can be black. The generated type should be blank, so as to have a blank canvas, so to project onto. Very good, we can click OK. And the color space should be sRGB, since we project the color values from a texture, which consists of non-linear color values intended for display, and not for light calculations, etc. For the baking to work, we should not connect this as of yet, so we'll keep this here. And then we can go back into the layout. And now, since we preview this with the texture color, and the only texture that it is consisting in the material that we previously added an image texture node to, is the blank, totally black texture, then of course this will be previewed black, but that is of no concern as of now. It will be changed when the projection has been completed. So we'll save the project, and we'll go to render settings, make sure to change the render engine to cycles. And then we'll go down here to the bake tab, and the bake type should be only the diffuse, since we're only interested in the color values. There should be no direct or indirect lighting contributing to the baking. It should only be the color of the texture. We want to use the selected to active mode here, so that if we enable the visibility of the original mesh, then we can select the original mesh. And then we can, with control, holding control, we can select the to be projected as well. And now you see here, with the light hue overlay here, that the projected one is the active, and we have the original selected as well. And with selected to active, that is as expected. Right, when defining the maximum ray distance, one has to take into account the dimensions of the imported mesh. These are not in any way one-to-one with real-world scale, so one has to consider this, that this is it is rotated around the x-axis as well. So the Z dimension here, it is not the world z, but it is actually this longer horizontal axis. But so it's about 87 times 47 centimeters. And then a suitable maximum ray distance would perhaps be 0.1 centimeter, so 1 millimeter. Perhaps we can up this to 3 millimeters to allow for the ray to be projected to extend a little further. Alright, when it comes to the margin, that should be the same as we, or not the same, but in MeshLab we define that there should be 2 pixels border between each triangle, and thus the margin here should be 1 pixel. Alright, with all of those settings set, we can save the project, and baking will take a long time, but you will, unlike all the other previous steps, you will see actually a progress bar here. So we can click bake here, and you see here that there is a progress bar here, and will allow it to finish. Alright, with the bake completed, you can hide the original collection here. And already here you see that it didn't work out as we wanted. And as you see here, we did not manage to project it adequately for a large part of it. So what we will do is to rebake it. So to make sure that all the projected rays are adequately projecting, we should use an extrusion here. So take a value of 1 here. It might seem excessive, but according to previous experience, it works. And then you can leave the max ray distance at 0. 0 means that it will project the ray without limits. All right, the margin should be 1, as we define in MeshLab. And then we can make sure that we first select the original and then the to be projected. With the projected being the active object and having the original selected, we should click Bake. All right, and it says it bake and map set to internal image, make sure to save it externally or pack it, and we will after we have verified the results. So we'll disable the visibility of the original. And we see here that we have results that are quite adequate. We see that there's a lot of spilling, or what one might say. Let's see if we check it out in rendered. And then, of course, in rendered, it did not show with the texture applied, because to bake properly, you will need to have this disconnected. Otherwise, there will be a circular dependency, which will disturb the baking. But now, having already baked it and not intending to bake, we can just check here with by connecting it to base color and going back to layout and switching view mode to rendered. There's a lot of these black small spots here. We can try once again only changing the margin value from 1 pixel to perhaps we can overdo it at 8 pixels. Let's try that as a first instance. And the reason why we see the texture here, even if it's not connected, is because we have this texture as color in the solid view mode here, and that takes any texture that is in the material. And as you saw here, even let's see if we have this selected, even if we disconnect it here, it is still there. Let's first try with 8 pixels margin and see if that solves the black splotches. Selected and active. 8 pixels. Let's test. All right, let's test to hide the original. Yeah, that was much better. That was much better. Now we actually got rid of those. You see here that the cage of 1 meter was excessive, because if we look at the original facade here, it does not have any leaves on it or foliage. And if we look here, you can see that it has been projected there. So increasing the margin to 8 pixels solved the areas of splotched black splotches around the vertices. But we'll need to fine-tune the cage amount here. So now we have 1 meter, which of course is excessive, but it was meant to test out if it worked, and it did work. Previously it was many areas completely black here. But now it works. So let's see if we can take Alt A, and let's see here if we can take an extrusion distance of perhaps 0.00, so 1 centimeter instead of 1 meter. Let's test that out. Show the original, click on it, and control click the to be projected so that it is active, and then we'll bake again. Oh, but make sure when you bake so that you don't have a cyclical circular dependency that you in shading, disconnect this, but it's already disconnected. Good, because you can still preview it here as texture color in the viewport shading for the solid. All right, so let's bake. All right. Let's see how this went. Yeah, now we got rid of the of this tree being projected on this. Let's see here if we have any other areas of... one could really say that we have one issue here, but I think that that's also at least slightly here. It's no problem with the texture actually, but it's definitely a problem with the facade, with the topology of the facade. Let's check if we have any black areas here. I can't see any, and given that, we could decrease the extrusion amount even more. So let's see here, if we make that visible, it's selected and the projected as active. So here I'll control click, make sure that it's active. And now we can, let's see if we have this as 0.5 centimeter, so 5 millimeters. And then we'll simply bake. All right. Let's see here if we hide the original. Yeah, now you see here that it's not as excessive. It's a little actually, but it's less than before. And do we have any black splotches? Not that I can see. We could bake one more time and reduce the extrusion amount even more. But I think that the one thing that we need to prioritize now is the actual resolution of the image. Because if one compares the projected texture that we have now, that we have baked in 8K resolution, with the original textures are comparatively in a much higher resolution. One could really see that on the tiling on the roof here. Yeah, sorry. Yeah. So then the next thing that we should fix is the resolution here. And the situation that we have here, concisely put, is that the original photogrammetry mesh retains a comparatively high resolution since it consists of many individually unwrapped pieces of mesh, each with their own texture image. And that means that the sum of all parts can be of a very high resolution. I think we saw that previously that, was it this portion here? That this was a single mesh, an individual mesh with its own texture and thus unwrapped individually. And of course, that can contain much more resolution, much more texture data per inch or per square centimeters. And of course, such a solution with individually unwrapped parts, each having their own texture, can result in a much higher resolution sum of all parts than if we look here at our projected, than one that has one single 8K texture for all of the mesh. There is of course a difference in there. And if we think that this is subpar, which I think it is, at least if we zoom in further than this perhaps, then we have two options. We can either, because the UV space is constricted, as long as you only use one texture, you are constricted to the UV 0 to 1 space. And the more mesh faces you try to fit in one UV 0 to 1 space, the more compact or the smaller portion of the total area those faces have to occupy to be able to fit everything in one texture. And one thing we could do is to simply pick a portion. Let's say we would pick out this portion of the mesh. We would delete everything outside of this, and then we would re-export this portion only to MeshLab, unwrap it the same way, and import it and bake it. Thus, each individual triangle, each individual face would occupy a larger portion of the UV 0 to 1 space. That could be a viable solution. But the other way of solving this is to simply allow to increase the resolution of the texture. And an 8K texture is a very high resolution texture, so it might not be advisable for the computer's processing power to go upwards of 8K. But in this case, we're just going to test it just to show you the difference in resolution it gives. So to do that, we'll go to shading. We'll make sure to select our to be projected mesh here. And here we have our node here with the untitled texture, image texture. That was the 8K texture that we projected to. We'll create a new one here. And this one should not be 8K, but it should be 16384, I think it is. Let's test it out. If we take 2 times 8192, then that's 16,384. Perfect. No alpha, blank. Okay, we can take the preliminary name as untitled 16K. Okay, very good. With the new image texture of 16K resolution selected here, we go back to layout, and you see we lost. It is the previously projected 8K texture. It's still kept internally in the Blender file as of now, unless we close it. But right now we have designated the texture 16K as of now, blank black texture. But we will project the color values of all of these textures onto it. All right, so select this one, control click this one, and let's make sure to retain the extrusion distance is based on the actual geometry and not on the UV texture, but the margin is of course on the depending on the texture. So we'll increase this, since we double the resolution from 8K to 16K, we'll double the margin to 16 here. All right, and then we can bake. All right, let's check this out. So we can hide the original. Wow. Yeah, I am totally satisfied with the resolution of this, at least for the scope of this tutorial. We don't see very clearly the individual tiles like we did here. They are very clear, but I'd say that they pass on a certain distance off as all right. When you are satisfied with the quality of the texture that you have baked, make sure to save it. Go to the shading view mode, go to the shading workspace, and then here in the image editor, you see here, it's an image editor. Make sure that you select the untitled 16K one. And here you see the texture. And as of now, it's only an internal image texture. But to save it, you go to this option and click image. And then you can save as. And yeah, we're in Blender here. And as of the file format, you can choose, of course. PNG has a non-lossy compression format, so it might be adequate for most users. If you choose JPEG, you will get a smaller texture file size than with the PNG. You decide which format you want to save it to. I think for this tutorial purpose, I think a JPEG is perfectly fine. I'll just make sure that it's 100% quality. And everything looks good. And then perhaps we should have a more suitable name here. So this is a texture of Google Maps photogrammetry KTH architecture school. And it's 16K. Take the time to copy this file directory so you can easily go there as well. Save as image. Right, it saves. Now it's saved. We can open a file explorer window here. And we can go to the directory where we saved it. And here it is. Very good. And this texture, it might look a little confounding, but it is properly mapped to the unwrap that we did in MeshLab. And given that we export the model from, given that we export the object from Blender with its texture coordinates retained, it can be imported in Rhino or any other program. And as long as you in that software's material editor assign this as the diffuse or the base color, then you will get similar results as here in Blender. we can actually, just to try it out, we can take this, select this, file, export, and I think for Rhino OBJ is totally fine. We can export an OBJ here. And we previously exported this so as to import it into MeshLab. We will actually export this as a little lighter variant, because I think this included lots of information that is not going to be needed. So I'll make sure that this says static mesh and Google Maps photogrammetry, ATHA. Very good. And of course, this is not scaled in any way, but here in Blender we don't have any reference as of now. And if we import it into Rhino, perhaps we have, and then you can scale it as you want. Let's make sure that we limit to selection only, and only OBJ objects, and no transformation. And then the geometry, we will not write normals. We will of course include the UV coordinates. We will not write any material. And the modifiers, we do not have anyone, so that can be left checked or unchecked. All right, let's see, because I think that this will be a slightly smaller file size since we don't include the normal directions, since it is flat shaded anyway. All right, now the OBJ has been exported from Blender, so let's start Rhino. Here we simply import this one. We can check here if they were of different. And here we can see that the file size difference was reliable, but anyway, we open that, and then here everything can be left to default except this one. Make sure to check map object Y to Rhino Z so that it is imported correctly rotated, or as we saw it in Blender. All right, and I'll maximize the perspective viewport here, and click outside in the void to deselect it, so as to see a little more clearly. We're still in wireframe mode, so let's go to shaded view mode, but then it will generate render meshes, so that will take some time. Or actually did not take any time, because of course this is imported as a mesh, so there are no render meshes to import. All right, looks good. We can try to check out with rendered, so as to get rid of the edges here. I wonder if this was as noticeable. It was not as noticeable in Blender as I remember it there, but we can simply check that. Yeah, it's actually quite visible here as well. It's a bad scene, but nothing that is not in the original geometry. Very good. So now we're in the render view mode, and we can click on the objects, and we can click on the material here, and we'll use a new material, and we'll use a new custom material, and the color should be a texture. And then we'll go to where we saved the texture. It was here, and then we open it. All right, I'll deselect the object. Oh wow, yeah, that was nice. All right, so here we have imported the Google Maps photogrammetry meshes as well as their textures, but projected to a duplicate of the meshes joined, as well as a baked texture, so one single texture instead of thousands of small ones. And the results are, well, let's just say that they are adequate enough. And this, of course, is in the wrong scale. It's in an arbitrary scale, depending on the camera zoom in you were in Google Maps. But this can be, of course, fixed here in Rhino if you either have a reference, if you have like the buildings represented by building blocks downloaded from the Stockholm municipality, or if you have building footprint curves downloaded from SLU, Geodata Extraction Service, or anything. Then you can scale it. Yes, now as like in this tutorial, perhaps we can scale it like this car. We guess is like approximately 1.9 over here. So let's see if we can select this, scale, and then the base point should then be one side, and we'll activate the vertex snapping here. So from this vertex to that vertex, or perhaps let's see if we can, oh, let's see. Perhaps we'll take another car with a little more vertices here. Yeah, very good. Oops. All right, so from that vertex to this vertex, right, as of now, it's a little less than a fifth of a millimeter. But now we'll make sure that this is, we can actually make the conversion to meter after this. So let's make sure that this is 1.9 millimeters. And now we can, in the millimeter scale here, we can change the units to meters without scaling it. No. Now the distance from this vertex to this vertex should be, yeah, around 2 meters. I am satisfied with that approximation as of now, simply to show this. All right. And positioning your camera in Rhino where you want it, and then make a render. And despite all the limitations and the artifacts and the areas of lower quality and the blatant seams, one could be pretty adequately happy with the results, given that this is only used for reference. Remember that the data itself is copyrighted both by Google as well as the companies that deliver the data to Google, so this should not be used commercially or non-commercially, but only for your private use. But for your private use, this can be pretty helpful. And this was one example of the workflow that you can apply to these photogrammetry meshes from Google Maps. But I think that it is not inappropriate to end with some images of Benjamin Bardou, who has been using these tools to make artistic renditions of Paris, Tokyo, and Venice. Thank you for your time.